Over the years, there have been a number of temperature delta O18 relationships that have been published. They're all, as I said, they're all empirical. They've done on mollusks. They've been done on foraminifera. They've been done on inorganic experiments. They've been done on corals. They all kind of look very, very similar. But for the purposes of application, okay, researchers found that handing an alpha fractionation equation to the community was not optimal because people just freaked out when they looked at temperature-dependent fractionation constants and having to work with something in degrees Kelvin squared. And so everybody started working with the fact that in the ocean we're dealing with a narrow temperature and it can be approximated by a quadratic equation. Hence, we wind up with quadratic temperature O18 relationships. For those of you in here who use this, I need to point out two things. I'm not going to belabor this point because most of you don't care, all right? But you'll notice that the parameter inside, the variables inside here, the delta O18 of the calcite and the delta O18 of the water, okay? Offline, I'll explain the why of what I'm about to say, but right now, suffice it to say that if you ever use these equations, delta O18 calcite is the delta O18 relative to PdB. Delta O18 water is the delta O18 relative to SMO, okay, all right, which makes absolutely no sense since you know there's a 30 per mil offset thereabouts between the two of them, but that's PdB, that's SMO, and you have to put a subtle correction in there, subtracting something between 0.2 and 0.27 from that delta O18 water value, so put that in parentheses, based on when the equation was published for a reason that, as I said, if you're interested, I'll go into it later. It'll take me 15 minutes, and I don't want to do that right now. Okay, so just be aware that you don't convert the water to PdB or the PdB to SMO. You use the PdB value and the SMO value in these relationships. And we get beautiful empirical calibrations with this. These are forams grown in the laboratory, delta O18 calcite minus water, and actually I have to fix this because it's really not versus PdB, that is SMO, okay, and versus temperature, and you know, our errors on the temperature estimates are below a ½ degree with these calibrations. This is a new calibration we have for Orbuline that we're working on a paper right now. All right, along the way, and this is sort of one of those things that you hope you stumble into through your careers. I call it the serendipity factor. You know, it's very, very difficult to get an idea up front and hit a home run because everybody, you know, ideas, everybody's thought about ideas. You have to basically stumble into something and recognize that you've found something that is not correct and not ignore it by saying, that didn't really fit my hypothesis, so I'm going to ignore this. What I'm talking about is the fact that during my years of my first PhD student, Brian Bemis, okay, we started analyzing foraminifera that we grew under highlight and foraminifera that we grew in the dark. Okay, so effectively symbiont photosynthesis, no symbiont photosynthesis. And because the mass spec that we had around, around 2000 could really measure small samples and we had really good precision, we were able to demonstrate that there is about a 0.3 per mil offset in O18 between foraminifera that grow in highlight and grow in the dark. And nothing in that oxygen isotope relationship does it say that physiology should have an effect on the oxygen isotopes. Okay, because organisms don't use oxygen per se. All right, so this became one of those kind of scratch your head types of things. And for a variety of reasons that had nothing to do with the experiments we ran, we sort of discovered the reason. We went in with a bad hypothesis and we discovered what was going on. And effectively, there is a third parameter controlling oxygen and carbon isotopes, which kind of throws a monkey wrench into a lot of paleoceanographic reconstructions that nobody yet deals with. All right, the first is that if you take a look at the carbonate ion concentration in seawater as a function of pH, so this is effectively the Bjorn plot, from about 8.2 to 8.8 pH, it's pretty much linear. Okay, this is a logarithmic scale, okay, but this gives you a linear relationship. So as you increase carbonate ion, basically what you're saying is you're increasing pH. That's the reason because most people don't think in terms of carbonate ion. Okay, remember carbonate's a part of this total CO2 relationship. Well, what we discovered that as we change the carbonate ion concentration of the seawater in which we grew these foraminifera, the shell delta C13 changed dramatically. Okay, so these are guys grown in the dark, these are guys grown in highlights, so we're not dealing with physiology here. And as you increase the pH, so you're getting higher carbonate, the delta C13 value of the calcium carbonate gets more and more depleted in carbon-13. 4 per mil in the lab without changing the delta C13 of DIC, temperature, light, anything, just the pH/carbonate ion concentration. Along with this, the oxygen isotope values changed. Okay, and we also saw this dramatic drop in the delta O18 just by changing the pH of the water or the carbonate ion content. Now this has dramatic importance to going back in time to times when atmospheric CO2 was much higher, ocean alkalinity was different, there could have been much higher carbonate, differences in pH, because what it does is it suggests that all the relationships that we've developed, whether it's for corals or sclerosponges or foraminifera, anything that calcifies, okay, you have a starting point with the pH of the ocean, the carbonate ion content of the ocean at that time, and then temperature affects it from that point. So if you change the pH/carbonate ion as you go back in time to the age of the dinosaurs where PCO2 might have been 2,000 ppm, okay, that baseline's changed, which can have an effect on what the temperature of the water was as you go back in time. And we've been dealing with this, and it explains some of the offsets that we see from other proxies. But the question is, why does it happen? And when we published this paper in Nature back in '97, you know, it was one of the kind of the, call it the home runs that the lab produced, okay, we didn't have a mechanism. And then a young postdoc by the name of Richard Zeeby, okay, who happened to be working with the group but didn't say a thing while we were trying to figure this out, came out and he said, I know the reason. And he wrote a paper about a year or two later, a few years later, 2 years later. And what he said was, and I'm convinced that he's absolutely right, and it also opened up some really interesting research areas, okay, was that if you take a look at the different species of carbon, when they're in equilibrium with water, what you find is that carbonate, the oxygen in the carbonate, is about 18 per mil enriched relative to the delta O18 of the water. This is all in SMO space now. Bicarbonate's about 35 per mil enriched. And the CO2 itself is about 40 per mil enriched relative to the delta O18 of the water. So what happens when an organism calcifies? Okay. And what Richard reasoned was, if an organism takes a vacuole and it takes a sample of the water that it's living in, that water is going to be composed, okay, of some amount of carbonate and bicarbonate depending on the pH of the water. And as the pH rises, the carbonate ion is going to increase, the bicarbonate is going to decrease. So if we assume that what an organism is really using to make calcium carbonate is not carbonate itself, but carbonate and bicarbonate both, okay, and what they do is they pump a proton out, so now everything's carbonate. There's no time to re-equilibrate the oxygen species with the water. So what you're winding up with is a mass balance of the amount of carbonate and its isotopic composition and the amount of bicarbonate and its isotopic composition. And when he plotted up, okay, this sort of mixing model as a function of pH, here's what he predicted, okay, the delta O18 should be relative to the water, and here's the data we got in the laboratory, okay, and he was able to show that it looks like what's happening is these organisms are able to use carbonate and bicarbonate in proportion to their availability. And this really opened up and answered a lot of questions, because if you look at corals and you look at coccolithophores, everything that calcifies, you have a relationship between oxygen isotopes and carbon isotopes. Remember that carbon isotopes are also offset as a function of pH. It's actually about a 3-to-1 ratio. That 3-to-1 ratio exists across not only the biological systems, but Brian Bemis, who was my PhD student as we were writing this paper for Nature, walks in. We have been reading the old publications, and a paper by McCrae in 1950, one of the Urey people, okay, he had written a paper, and in it, okay, Brian says, have you read the McCrae paper? And I said, yeah, I read it. You know, I'm reading it like tonight, and he says, well, it has the first temperature O18 relationship. He says, yeah, get past figure 1, look at figure 2. And when you look at figure 2, you see in 1950, he has this plot that shows carbonate ion concentration against delta O18, exact same slope that we have. Okay, 1950, first paper ever, they had it in 1950. The entire field forgot this. They never read the paper. They just would go and cite McCrae 1950. Nobody ever went back and read those papers. Read them. You can't believe what's in them. People just cite them. They don't read them, or nor they, you know, they actually know what's in them. So back in 1950, the Urey lab had this, and nobody followed up for the next 70 years. We just rediscovered what they had shown back in 1950. All right, so that gives you a sense of what's going on in carbon and oxygen space, and this pretty well is established now that other calcifying organisms respond the same way. Okay, respiration tends to decrease the delta C13 of the calcium carbonate. Photosynthesis increases it, and the oxygen isotopes are a function of temperature, but they do have this offset that's related to microenvironment pH is controlled by that balance between respiration and photosynthesis.